Okay, so now we are in week 11. We try to clear chapter 7. We already clear chapter 6. So today we do chapter 7. Next week, weeks 12, we will cover chapter 8, new chapter. Then your lab report due next week, Friday, 5 p.m. The time I will follow Canvas time. All right. So after 5 p.m., I will not mark your lab report. I will mark as no submission. All right. Then you get 0 marks if you submit after 5 p.m. Okay. Week 13 will be your test 2. Test 2 will be on Friday. Okay. So if you miss it on Friday, there will be no retest. If you miss test 2 on Friday, there will be no retest. Huh? Which one? Test 2. Test 2 will be in class. Will be in class. So you'll be on. Then your assignment, individual assignment, will be due on week 13 Friday also. Right. So I already send you the Canvas message. The due date, exactly due date already on the Canvas. All right. So again, same. Week 13 Friday, 5 p.m. No, not 13. 17. Okay. On the Canvas, your assignment due on 17. No. Means this assignment due 17. Okay. Lab report next week. Yes. This one is after Deepavali. Okay. The report next week is 10, right? In the Canvas, I write 10, right? Okay. Then week 14, we do revision. Okay. Yeah. So take note on the due date. Follow the one that I send you in the email. After 5 p.m., I won't mark. I will just assume you are not interested. And very high chances I'll see you again next semester. Okay. So now we go to chapter 7. By the way, go and check your attendance. Some of you, your attendance is below 80%. So you're being barred from final exam already. So need to go and check your attendance. All right. So your test 2 will be cover CL3, CL4. Okay. CL3 will be on kinematics problem on rigid body. CL4 will be on Newton law, work energy equation, and principle to solve rigid body. Okay. Okay. Now, okay, just before we go into chapter 7, there are some recap. Chapter 6, we talk about rigid body. What is rigid body? There will be 3 motion: translation, rotation, and general plane motion. And we are using all the force equal to MA, but at the end of the session, you know that we're focusing on center of gravity. Okay, so chapter 6, what is different is rigid body, we always focus on the center of gravity. You will see G in the question. So F equal to MAG. Okay, and all the moment in the free body diagram will same like in your kinetic diagram. Okay, another one, you need to use all the moment equal to I alpha. Okay, it can be G, it can be O, it can be Then what is I? I equal to Ig plus md square. Okay. And you need to link V equal to omega R. You need to link acceleration with AN plus AT. What is AN? You need to link AN to rotational because rigid body, it will rotate. It will rotate. Once it's rotate, it will be in a circular form, right? So AN will be omega square R. AT will be alpha R. Okay, so these are the four things. Okay, so your free body diagram for chapter 6. Free body diagram for chapter 6, you have free body diagram and kinetic diagram. Over here is all the force. Over here is motion, which is V and A, but in your diagram, you'll be seeing M, A, G. Okay, why? Because you need to convert MAG is what is force. Multiply by the distance, you get moment. The intention of chapter 6, we are looking at the moment diagram. So in free body diagram for chapter 6, we're expecting you to put the D in the free body diagram. You're converting all these force with the D into moment. Okay, so this one is a free body diagram moment. This one is kinematic diagram moment. This one. Okay, so these are different compared to the previous particles chapter. Rigidity, you look at what happening to the center of gravity or reference point. Okay. Right. Now, chapter 7 is combine what you learned in chapter 6, go into application of what you learned in chapter 4. We'll talk about energy, we talk about work, we talk about conservation of energy. So same. Previously, if you talk about energy, we deal with kinetic energy and potential only. When you talk about principle, it must be principle of work and energy. So work is work. Work is force multiplied by time, right? Multiplied by time. Multiplied by distance traveled. Okay, must be parallel, so you get positive value. Okay, so this is what we learned previously. Yeah, F and S must be parallel to get positive value. When you have conservation of energy, then means all the energy equal 0. Means before equal to after. Right? There is no change of, or you write before equal to after. Okay. So what is different here will be in rigid body, you are learning force and moment. So there will be a moment that converted into energy and work. Previously, particles, you don't see moment because you are not considering the effect of weight. Okay, effect of weight will acting on the center of mass, the G point here. Okay. Okay, so just recap. When you see this diagram, you know that this is a rigid body with a loss of point X and Y, point P, reference interest point X, and there's a velocity, point P, and there's a rotation of omega with its rotational velocity. And this is the interest point I. So you have your VI vector. Okay. So what is the same thing between point P and point I is the omega or alpha. Okay. What is the same thing that between P and I is the omega. How you link this omega by using IC method. Okay. When you have velocity, you use the IC method, draw the IC point. Okay. If you don't know what is IC, go back to the chapter 6 recording video. Okay, you put a ruler here, draw one line. Put your ruler here, draw one line. There will be intersection here. Then you draw from IC. You measure IC to there. What is the R? V multiplied by R. V equal to omega R. So you want to find omega. Put your R to the left-hand side. V divided by R, you get your omega. Okay, V divided by the R, get your omega. Okay. Okay, the rest you read. Same. What is the equation for kinetic energy? P equal to half mv squared. Okay. But because we are looking at the rigid body, we need to do integration of your mass. Okay. Now in particles, we don't do integration because we sum up everything in one body in particles. So when we come to rigid body, we need to do integration because this is a body. We need to sum all the small component into one big body. Okay. Okay. So the first equation for today is the kinetic energy, which is half mv squared. What is different is that you need to do integration for the mass. Okay. Then you know that your VI, you have VI equal to VP plus VI stroke P. This is what you should be familiar with. If you draw the vector diagram, okay, you know that we have a cheat code here where you convert VI slash P means VI stroke P. What does it mean? We refer from where? P, yeah. So refer from P to I will equal, you convert this slash into VI minus VP. You can rewrite the equation VP equal to VI. Okay. It should be minus VI stroke P. Wait, let's continue these slides first. VI I stroke P. Okay, so this is a theoretical equation. Okay, this one you read lah. So VP, you can split into I and X direction, Y direction. So your VP become I and J direction. Then VI stroke P is this one. Okay, VI stroke P is omega multiplied by the R. VP equal to omega R. V equal to omega R. Okay, omega is this one. So use the right hand rules. You go outside screen, so positive. So what is your R? R is here. So R is X plus Y, but with the I and J. Okay, but in this module, you don't need to use the vector method, right? So you do multiplication at the end. You arrive at very, very lengthy derivation, but I won't ask you on the derivation, right? So you do the derivation, then you do the squared, okay? So dot and cross is different, huh? It's a difference between vector A cross vector B, sorry, vector A cross vector A, and vector A dot vector A. If it's in the same direction. Okay. If AI cross AI, you get 0. If you dot, then there's a number there. Okay, so this one you see, blah, blah, blah. At the end is a quite lengthy equation. Okay, so you derive kinetic energy of mv square. This is your v. This is your v. So you know that you need to integrate. So this one integrate this one integrate this one integrate this one, and so on. So you have 1, 2, 3, 4 components mathematically. Okay. Okay, so there are 4 components. Okay. The derivation step, you go home and read. So what is important, I highlight, when you look at rigid body kinetic energy, you have 4 things happen inside there. First, your mass will do something. This is what you learn in particles. Your mass will do something or create energy. Half mv squared. This is the your particle chapter. Second one, you look at center of mass already. Second, center of mass G will give you some energy also. So this one, when you look at rigid body, the center of mass G will do energy. Then the third one, because of mass also, we will consider moment of inertia. Moment of inertia will do something. So that's why when you press a brake in a high-speed car, the car will move, continue to move because of inertia. Even there is no energy given, but because of the previous energy carried onwards, it will continue to move. This is due to moment of inertia. Sorry, this is the last one. These two, the center one will be the center of mass because it's x and y. Okay, so just to summarize, just now I say 4 is actually can summarize into 3 components. So kinetic energy consists of 3 components in rigid body: mass effect, center of gravity effect, and moment inertia effect. You need to remember these 3 components on it. Okay. So again, particles only you see this one. Rigid body, you have another 2, which is center of mass and moment of inertia. Okay. Then this will be the equation that we will apply for rigid body in kinetic energy cases. Okay. So this is, you'll be familiar, half mv squared because of the mass effect. Then this 2 is due to center of gravity. So V is a V omega, and Y bar is the average distance from the center of mass multiplied by the M, okay, plus the Y component, right? And the inertia, half omega square IP. Okay. So when you have a special case where the P or your interest point is on the center of gravity, means this one, if you move your interest point to the center of gravity, means every time you solve your question, you move your interest point to the center of gravity, your Y bar will be 0, Y bar will be 0. Okay, so you can cancel the middle part. The center of gravity effect, center of mass effect will be 0 if you move your focus point from somewhere into the center of gravity of the object. Okay, you will see this one because you move away from the center of mass. There's a point P here. That's why you see Y bar, X bar. Okay, now at the end, most of the time you only need to use this equation, which is, if you look at kinetic energy, it will be half mv squared plus inertia effect. With this, you need to remember one more equation at the back will be half mv squared plus 1/2 omega squared Ig. This will be the chapter 7 equation. So kinetic energy will be have three components. So will be mass component, will be center of gravity component, and inertial component. So because you're moving your G, your interest point to G, this one becomes 0. So your T will become half m v squared, and remember you're focusing on the center of gravity there already. So you're focusing on the velocity at the center of mass. So your approach, now you focus on center of gravity already. Okay. Then this one 0, and inertia will be half omega square I at the center of gravity. So how you find center of gravity? Very easy. IG will be from your table. This one you only need to read from table. How to find omega? You find from the velocity. What is velocity equation? Velocity equal to omega r. Okay. You want fast way to find omega? Again, use IC method. Go and find the V of 2 point, then measure or draw on the free body diagram. You should able to find your R. Once you find your R, you can find omega. Okay. So this one always positive. Why positive? Oh, you know that velocity is vector. No matter whether to the left or right, you get negative value, but you square it, you still get positive value. Okay. This one also same. Omega, either it's come out from the screen or go inside the screen, you also square it, you get positive value. Kinetic energy in rigid body always positive. Okay. Okay, let's look at, because of rigid body, you have three motion again, three pattern. One is translation, rotation, and general plane. Translation, you have two types. One is linear, one is curvilinear motion, right? So when you do translation, let's say we take this body again, because we don't want to solve question involve the center of mass, we already take out the third component. Initially, we need to write the three, but we will pull all our focus point to center of gravity. So we are focusing on center of gravity, G, and you draw a velocity there. Then there's a velocity. Okay. So if the translation do not have rotate, right? So when you don't have rotate, you don't have omega. This is angular velocity. You do not rotate, you do not turn or something. So when it's translation, this one 0. Okay. So it depends how you want to analyze. So you need to observe how the object move in rigid body chapter. Okay. Then if it's rotation, like this case, about a fixed point. So for example, this one rotate at a fixed point with the R and V. You know that the how to find omega, right? V equal to omega R. So you take velocity divided by R, you get omega. Okay. So once you have omega, you need to use two things. Okay. So you have two, you need to write this equation. Okay. So again, your kinetic and energy equation, you have mv squared because of mass, and you need to consider the inertial effect. We consider, is there any rotational or not rotational? Is there any rotational motion with omega or angular motion? Then you have the angular motion component. Okay. So again, this is just a highlight. How to find omega? V equal to omega R, right? So we just want to change everything in the singular parameter. So you can write this one, or you can extend. This is actually your step in the exam. So you write this one, then you write V equal to omega R, you convert Vg, this Vg in the center of mass, into term of R and omega. Okay, R and omega. Because you don't want, sometimes you want to find the omega, right? Or sometimes the omega is missing. Okay. So when you combine, you factor out the omega, the angular velocity, you'll get half m plus inertia equal to omega square r, omega square. So you can change your equation by using v equal to omega r. It depends on what you want to solve. So this is just one of the solution. So when you need this one, when the question give you omega, do not give you velocity, straight away you this one. Yeah. If the question give you v, you need to find omega, then you use this one. But this is more direct lah. It's more direct. Okay. It's either way lah. You can find, once you have either one omega, you can find v. You have v, you can find omega. It's the same. It's a direct thing. Okay. So this one you read lah. This one you read. So you can memorize also can. It will be half omega square m r square plus I g. Both I highlight with a capital G here, sub capital G. We are now looking at the center of gravity. Okay, so you know that this one is actually your I. Why? Because your I is equal to IO plus MD square. Now you're referring to, IO equal to IG plus MD square. So you are converting this one into IO. So for rigid body, in a short or simplified method, or simplified way of writing it is IO omega square. If the object is rotating, or there's an angular rotating. So this one, only when the object is rotating with the omega. If it's translation, then this one. Okay, translation is this one. If the translation is only this one. Okay, if the object only move translation, then only this one. This one don't have rotation. You move in this way, straight line. So don't have this one. So only have this one. Then if the object is rotating with angular, then it becomes this equation. Yeah, so don't confuse between this one and this one. Okay. So this is when you have a angular rotation. Okay, general plane combine two, translation and rotation. So when you have two rotation and translation at the same time, then you need to use the complete equation. This one, complete equation. Okay. This whole thing, this equation, when you have a general plane motion, you need to use the overall. Okay. Or only one equation you memorize, like what I write on the screen here, on the whiteboard here. Half mv squared plus half omega square ig. Okay. So when you use the full equation, this is for the general plane. Means you have rotation and translation. but you need to be careful on the value of your IG when it become general plane. You need to when they because you need to refer to the, if you refer to a certain point, you need to convert your IG in terms of IO. Your IO will become IO plus MD square already if there is a different point. Okay. Okay. So another way is writing is you can using IC omega square lah. Okay. Okay. So in general plane, if you're lazy, you can just write IC omega square. So this is general plane. Okay. So translation, angular motion, general plane. Okay. Okay, work. We already know what is work. Work is force. As long as the force travel with a path, there is a work. And look back at the previous slides, there are some situation force do not generate work. Go back to the previous slides. There will be a scenario where force do not generate work. Okay. Again, when you generate work, only your force go parallel with the distance. Okay. So this is just a derivation. Don't confuse with the R. It's actually a distance traveled. Work in previous chapter, we use capital U. Okay. So U equal to force multiplied by distance traveled. Same with this one. So we just a general equation where you can convert your R into S with the theta. Okay. So this one is just a recap of a section of a circular body, theta, S and R. S equal to R theta. So this is F cos theta, right? Okay, so I need to highlight here, we are focusing if you use theta. Theta is between the tail of the force and the displacement. Means here, this is the tail is at the back and the force. Give you the example. Okay, so this one you learn in your particle chapter. If you have a constant force, for example, Fc here, and your object move in this straight line, again, you can split your force into vertical and horizontal, horizontal. So you can go down and go to this direction. So you know that when the force go 90 degree with the path, there's no work done. Okay, only this component. So this one you convert into F cos theta, which is parallel to the path. It will generate force. Sorry, to generate work. Okay. So the same principle apply. When the force go parallel with the distance, then you generate work. Make sense? Okay. Okay. Now the next one is weight. Weight will do work, but this time remember that there is a positive, negative direction. Okay. Work go downwards means the weight lah, Wmg. Go downwards. So the distance from here to here is positive. But if I put a datum here, I point the arrow up, it will be negative. The work will be negative. Okay, so just be careful. If you see the question already point a arrow there for you, where is a positive H or positive Y, remember that is a positive direction. And positive direction, your work negative already. This will need to highlight this one. So normally this will be the tricky part in the question. Okay, even though there's no datum words in the question, but it will show you arrow. Where is the positive H direction or Y direction? Okay, so this one on the slide here, I already explained why there's a negative there, because your datum is below and the arrow is pointing from the below to the top. The positive direction of Y is going up and your vector of your weight is going down. So the distance traveled and the force is different direction. So that's why your work is negative. Okay. Next one, spring force. Spring force will be the same, like what you learned in your particle chapter. Spring force will be negative. It will be negative half kx squared minus half kx squared. Okay. This one I need to highlight what force that do not do work. If you look at this diagram on the below here, does the W do work? If you have a round body, does the W do work? Why? It's perpendicular. No matter how this one rotate, move to the left or right, W always pointing perpendicular to your distance. This object moving to the left or right. In this one, omega is this way, so you rotate to the right. Okay. And what else? Normal also doesn't do work. Friction do work. Friction do work, and so on. So these I need to highlight here. Okay, so here I need to highlight this one. In normal case, friction will do work, but I need to highlight this one. A frictional force acting on the round body at its roll without slipping over a rough surface does not do work. Why? Why? Why frictional force for round body without slipping is work is zero? Why? But to think again, what is work? Force multiplied by distance traveled. On round body, where's your friction act on? On round, smooth round surface, although it's a rough surface. This is, let's say, your round body. Why your work on the friction is zero? There's a friction, but why there's no work? Why? The clue is on the what I draw on the whiteboard here. Why? Why your work for the friction is zero? Why? Huh? Huh? Just now? No distance. Elaborate no distance. Contact point only act on one single point. Only one dot. 1 dot is a very, very small number. So F multiplied by small number equivalent to 0. Very, very near to 0. Okay, imagine one big cycle. The contact point only one. And all the time, friction force only happen on one point there. Although it's rotate. But we are more interested in the friction force at that point. It always happen at one point there. So your work is 0. For if the question purposely mentioned round body at its row without slipping, you see this word, don't consider work for friction. Don't suka add friction force for your work. For particle, yes. For rigid body, no. Or you can say, I think I mentioned this one also in particles. Yeah, particles friction on the round body also doesn't do work. I mentioned this one in the particle chapter. Okay, so I need to highlight this one. When you see, if the question come out, like 2 drum, you know that in civil there's lots of when you repair road, there's one vehicle that have 2 drum. And it asks you this kind of application problems. It asks you to find work done by the rigid body. Don't consider friction force on the drum. Okay. Okay, so go a bit more. So another one. Okay. So the previous 2 slides is you're already familiar. Spring, weight, you're already familiar in particles. Now, what is different in rigid body? Rigid body, there is a moment appeared because of the center of mass. So when the body have a moment with its F multiplied by R, there is work done. Okay, so you know how to convert moment back to force, right? Moment equal to F multiplied by perpendicular distance. So if I give you a moment, you're focusing on the center of mass, you should be able to convert this one into forces. The static chapter or static module, you convert here to here. But in engine dynamics, you reverse the process. In engine dynamics, you calculate the moment created by this force and the distance. Then you draw free body diagram with the moment. In engine dynamics, you reverse. We give you moment, you reverse back to force and distance. Yeah. So this will be the thing. You just need to recall back how to find moment, how to find the force. Okay. So okay, the rest you read. Okay, now when you have force, you enlarge the body. When you have force, we are now, this is moment. We dismantle the moment into force and distance. So this is a center of gravity or center of mass. So when you center of mass, there is a distance r and a force. It is perpendicular. You know that this body will rotate. Right? Moment will turn the body. Right? So there is a change of displacement here. Right? You have a theta here. You know that how to connect the small circular section. S equal to r theta. So ds equal to d theta dr. Right? So S equal to r divided by s d theta. Okay, so at the end, you need to consider work done by the moment by this equation, right? Or in a more, okay, work done. Work done, you need to add one more because of moment will be m d theta. Meaning you look at the moment, what is the angle that it turn? You take moment, multiply by the angle it turn, it will give you work. Means work done by the moment is based on how many angle it turn. Moment multiplied by angle, you will create work. This one you do not see in particles. You only see in rigid body with the mass effect. Okay, so this is another new equation for today. Okay. Then because it's d, you need to do integration. Integration from theta 1 to theta 2. But basically, it's just a change of angle, differences of angle. Okay. Okay. Do you need break? Continue. Okay, we break. We continue 9 o'clock. Maybe 7 minutes short break. Sign your attendance.